Here we'll be looking at Chapter 9, Section 2, number 15, in working list problem. As I first glance at the problem, I already see that they've calculated the average and standard deviation of the two samples for us. So unlike number 13, where we had to calculate that all ourselves, we have that to save us a little work there. Right, the coaching staff of a professional football team believes that the rushing offense has become increasingly potent in recent years. To investigate this belief, 20 randomly selected games from 1 year's schedule were compared to 11 randomly selected games from the schedule 5 years later. Okay, randomly done, that means they're being done independently. They're not overlapping. The sample of information on rushing yards per game, run yards per game, is summarized below. In both of these, the sample size is less than 30, so we'll have to use the t-distribution instead of the normal distribution for our test statistic. All right, so construct the 95% confidence interval for the difference in the population means based on these data. Okay, let's dive right in here. So A 95% confidence interval, which means our alphas could be 0.05. And with the difference in the population means, so mean 1 minus mean 2. And the way I did this, we'll just have this, the previous one is 1, the current one is 2. So look at that, so we're looking at the difference, and I can do these either direction at this point. For the confidence interval, that all will work out. So as we mentioned, since this is a small sample size, we will use the confidence interval distributional calculation that is there in this section of the book. So we have x1 minus x2, the mean, x bar, x1 bar minus x2 bar, plus or minus the t distribution of alpha over 2, and the square root of this sp squared, 1 over n1 plus 1 over n2, where this sp squared thing is that weighted n1 minus 1 times the standard deviation of the first sample, so the sample number plus the number in the second sample minus 1 times the standard deviation of the second sample, all that divided by the sample size of the first plus the sample size of the second minus 2. Let's go ahead and calculate that out first. So that's going to be our 20 minus 1 times 24 squared plus 11 minus 1 times 21 squared, and divide all that by 20 plus 11 minus 2. Okay, so that'll give us, when we do that one, we have continue working this, 19 minus 576, not minus, times 576, plus 10 times 441, and all that divided by, let's see, 31 minus 2, 29, and that's going to give us 529.4. Okay, so there's that value. Let's go back to our whole equation up here we have for our confidence interval. So we have our average of the first sample minus the average of the second sample, plus or minus. So this t statistic here, this t for the alpha over 2, this will be our alpha over 2. This will be a t at 0.025. That's that alpha divided by 2. That's what that we're looking at there. And the degrees of freedom, because with our t distribution we need degrees of freedom, and the degrees of freedom actually is this piece of the equation right here. So that gives us our degrees of freedom of 29. Okay, then we have that times the square root of our sp squared. This is this. So sp squared is 529. This is another one of those places where I went and I squared 529 the first time, but it's already squared because the SP squared is that value, 529. So that times 1 over the size of our first sample, which is 20, plus 1 over the size of the second sample, which is 11. So we're going to have minus 2 plus or minus. If we go look up in the student t-distribution table in the back of the book at a 0.025 down to the row for the degrees of freedom of 29. Let's see, that gets us 2.052. And if we work out what we have right here, this will be 74.53. So we're going to have minus 2 plus or minus 2.052 times 8.63. So if we look at that, that's going to be minus 2 plus or minus 17.7. So our confidence interval is from minus 19.7 all the way up to 15.7. So we're 95% confident that in that range is where the difference of the population lies. So 0 is in the middle of that range, so 0 would be no difference. So we're pretty close to no difference. So let's do our test statistic at a 5% level of significance to see how that works out. So for B, we're going to do a 5% level of significance test to examine whether the data on rushing yards per game provides sufficient evidence to conclude that rushing offense has become more potent in recent years. So just so my brain is working on this one the way I want it to be, I'm going to do this with, I'm going to do M2 minus mu1. So instead of the 1 minus 2, which we did up here, because we're trying to look at is the in the recent years. So if recent years has more rushing than old years, that means our mu2 is going to be greater than our mu1. So the difference, mu2 minus mu1, would be positive if I look at it that way. So what I'm going to say here for my first step in hypothesis testing, my null hypothesis is that mu2 minus mu1 equals 0. So we always come back to this, what's that difference we're looking at comparing to for our hypothesis testing when we're looking at comparing two different samples. And then my alternative would be mu2 minus mu1 is greater than 0. Now if I did it the way I had before, mu1 minus mu2, I'd expect it to be negative, so I'd be looking at it for being less than 0. So I can work that either way. So we're going to go 2 and 3 here. So I often put those together because I'm identifying what the test statistic is. In this case, the test statistic that's spelled out there in section 2 of chapter 9 for the comparison of two different independent samples that have sample sizes less than 30. I have to use this t-distribution one, so I'm going to have this be x1 bar minus x2 is the way that it's written. We'll talk about that again here in just a minute. Over the whole thing here again of SP squared times 1 over n1 plus 1 over n2. And in this case, what we're doing, as I said, I switched x2 and x1 to look at it the other way, so it would be positive instead of negative. So I'd be looking for the positive. It's how we want to play that one. So 114 minus 112 minus the 0, because that's the difference I'm looking for is the 0. And so I have that one there. And in the denominator, I'm looking for that same beast that we had up above, because back up here, so if I follow this back up here, I've got that beast right there, which if we looked at that and we calculated that, that was this whole square root thing, which wound up being this 8.63. Okay, so this is going to be divided by 8.63, which is going to be 2 divided by 8.63, which is going to equal 0.232. Now, if you look at what is my interval, the critical interval that I'm looking at. And here we're looking at our t-distribution. Since we have a one-sided test here, we're going to be looking at just the t-distribution on one-sided without dividing it by 2, which would be looking at where we had a two-sided test. So the degrees of freedom in this case for t, that's not a t, that's an alpha again. So t at 0.05 for that 5% level of significance at degrees of freedom of 29. Degrees of freedom was this same value up here. Let me scroll back up a little further. That in there, which gives us the 29. Again, let's delete all that stuff off of there and scroll back down. So 29. So if we look in our table at t for 0.5 at degrees of freedom 29, we have 1.699. So rejection zone is 1.699 to infinity. And so if we look here, our t value, so our t of 0.232 is not in the rejection region. So at a 5% level of significance, the current data does not support a difference in rushing offense in recent years. And I don't know why I put the ellipses out there. Probably because I was writing so scribbly, it was like I could even pull that one up. All right, so there it is. We do not have significant data to reject the null hypothesis in this case. So we go with the original. Oh, don't need to go up to a previous problem. Great, there's number 15.